Hi, Assalamualaikum warahmatullahi wabarakatuh. In this video, we are going to look at this particular idea, which is if we have x and y and we know that they are independent, then the result is covariance xy is going to be 0. That is a straightforward implication, but the reverse is not true. Okay, so this only works one way. That means only if you know that they are independent, then the immediate result is covariance xy is going to be 0, but the reverse is not true. So if you know that the covariance is 0, doesn't mean x and y are independent. So that is what indicated by this statement right there. Okay, so now we're going to look at a little bit of proving right now. It is quite simple. We're just going to show that if we know x and y are independent, let's say in this case discrete random variables, then we're going to prove that this statement is true, and then we're going to show that consequently the covariance is going to be equal to 0. Okay, so that's what we're going to do in this video. We're going to start off with a little bit of proving. Okay, it says here x and y are discrete and it is also independent. So this is the information given to you. And we're going to start with the left hand side, and we're going to show that the result here later on is going to look like what you have seen on the right hand side. Okay, so from the left hand side, we have expected value of xy, and according to the definition, if it is a discrete random variable, then we are dealing with double summation, where you have xy multiplied with the joint probability mass function fxy, and this is for this one here related to the values of y, and this one here related to the values of x. Okay, now what we have next is we have the information where it says x and y are independent. So that gives us a clue as how we can proceed with this one. And in the previous video, I've shown that when it is independent, that means the result of that can be simplified or can be written as this one we have. This one right here will become fx times fy. So that's the result that we get when we know they are independent. Okay, it goes back to the very basic idea of probability, which you have seen. Remember in the first chapter, for example, if you have A intersect with B, and if you know that A and B are independent events, then it will become PA dot PB. And similarly, if you have the joint probability of x and y, and if we know that x and y are independent events, so the result is going to be fx times fy. Those are the things that you have already seen in the earlier chapters. Okay, and we're just applying that result right here. So this is the result that we can apply straight away if we know that the random variables are independent. Now what we can do next is we can group x's together and all the y's together. So what we're going to do next is I'm just going to write down in terms of all the x together and all the y's together. So I'm going to have x times with fx, just rearranging this part, and y times with fy. Okay, now the next thing that we can do is you can see that for this one right here, we are considering the expression that are related to y. Okay, so these are the expression that are related to y. Therefore, this guy right here, it doesn't depend on y. So when it doesn't depend on y, we can consider that as a constant, and we can just take it out and put it outside of this process. So that's what happened. Okay, so we're going to consider that. We're going to take out, sorry, I'm just going to write down here. So what we're going to do is we're going to take out this guy here because it doesn't depend on y. So we can take it out, we can put it outside first, So we have x dot fx, and then here we have something related to y, and y dot fy. And based on that, you can recognize these two parts right here. So this is something multiplied with another item, okay, another expression, and we know that this one is actually the definition of ex. This is the definition of ex, and this is the definition of ey. So we have managed to prove that from exy, if we know that they are independent, the result is going to be equal to ex dot ey. Okay, so this part is done. Okay, for this one, this is done. Okay, that's it. And then we're going to move on to the next part, which is to prove that this statement is true. Okay. Okay, so this is what we're going to do next. We're going to prove this second statement right there. So we're going to start off from the left hand side. So from the left hand side, what we have is exy minus mu x mu y, and since we know that x and y are independent, what we can do is exy right here can be represented as ex dot ey, excuse me, okay, minus mu x mu y. So okay, and then we know that ex can be written as mu x, ey can be written as mu y. Okay, that's the mean of x, that's the mean of y, minus mu x mu y, and we have the same term right here against each other, so the result is going to be equal to 0. So that's quite easy to prove. Okay, right, so that's example 4.9. Basically, to show you this statement, okay, I go back to this important statement right here, which says that if you know the random variables are independent, if you know that x and y are independent, then immediately the covariance is going to be equal to 0, but the reverse is not true. And in the next example right here, we're going to show that the process of, if let's say you have the result of covariance xy is equal to 0, then we cannot say x and y are independent. So x and y independent? Well, not necessarily true, so this is not true lah. So okay, so this is not true, that's not how it goes. Okay, not true. Okay, and this is an example to illustrate just that. We're going to start finding what's the value of covariance. So we're going to show that in this example the covariance is 0, but then the two variables here are actually not independent. Okay, let's start off with finding exy. Exy is, according to the definition here, what we have is a discrete case. So we have a double summation xy fxy, and this is y from -1 until 1, so that's the value of y. And then x is also similar, it starts from the lowest value is -1 and it goes to 1. Okay, the next step is we're just going to substitute the value of x and y into this expression given here. Okay, so we have x from -1 times with -1. So y is also -1, and we're going to multiply that with -1, -1. The joint probability for x equals to -1 and y equals to -1. Next, we're going to maintain x at -1, but we keep on changing the inner part of it, which is the values of y. We're going to change all the values of y from -1 to 0 to 1. Okay, -1 with 0, f negative 1 0 plus the value of x is negative 1, the value of y is 1, and then f negative 1 1 plus. Now we are done changing the inner part. We're going to change the outer part. So the outer part is from x negative 1 to x 0, and we go back to the value of y. Y starts from negative 1. Okay, and then maintain the value of x at 0, and we're just going to keep on changing the values of y. So we have 0 and 0. Okay, so that's what we have. And then we are going to have 0 with 1, f01. Okay, next we're going to change that to the next value of x. The next value of x is 1. So 1 with negative 1, f1 negative 1 plus 1 with 0, f1 0 plus 1 with 1, f1 1. Okay, next we can cancel out things that are related to 0. For example, this one is going to be 0. This one also going to be 0. This one also going to be 0. This one also going to be 0. What else? This one also going to be 0. Okay. Right. I don't have a space to continue, so maybe I will just use this space right here. I'm so sorry. So I'm just going to use this space right here to continue considering this part. 1, 2, 3, and 4 items that are left to be evaluated. So for this one here, the result is going to be 1 times negative 1, negative 1. The joint probability of x negative 1 and y negative 1 is right here. So 1 over 6. 1 over 6. So this is 1 over 6. Okay, next this one is plus dengan negative, so we got negative 1. So f negative 1 1, f negative 1 1 is this one, so this is 1 over 6. Okay, next for this value we got negative 1, f1 negative 1 is this one, so this is 1 over 6, and then plus 1, f1 1 is this one right here, so that is 1 over 6. Okay, so basically this will be cancelled out with this one, this also will be cancelled out with this one, and the result of expected value of xy is going to be equal to 0. So that is expected value of xy, yeah? And we're not done yet, because in order to find the covariance, we need ex and ey. Okay, we're going to move on to finding ex and ey. So what is ex? So ex is this one, x dot fx, and the value of x starts from negative 1 until 1, and negative 1 until, let me just write it properly. Okay, so what we have is x is equal to negative 1. And I'm going to start off by constructing the marginal distribution of fx. And this is the value. Okay, so we can see from the table right here, if x is equal to negative 1, therefore these are the probabilities that you need to consider adding up. So we have 2 over 6, 2 over 6, yeah? So that's one is 2 over 6, which is actually 1 over 3. Maybe I should write down okay, this one is 1 over 3. Sorry, this is 1 over 3. Now when x is 0, the result is going to be 1 over 3. And when x is 1, it's going to be 1 over 6 plus 1 over 6 is 2 over 6, which is also 1 over 3. And you can see clearly that if you add them up, the result is going to be equal to 1. Okay, so that's one way to check that your probability distribution is correct. Okay, Now therefore ex is we're just going to substitute all the values of x into this expression here. So we have -1 with f -1 times f -1 plus 0 with f0 plus 1 with f1. So that's what's going on related to this formula given here, and then we can substitute the value of -1 and so on. So here -1, so the probability when x is -1 is 1/3. This one is going to be 0, and this one is 1. f1 is 1/3, and you can see that this will be cancelled out as well, so ex is going to be equal to 0. Right, now let's move on to finding expected value of y. So expected value of y, we follow the same idea. It's going to be y from -1 until 1, y dot fy. So this is the formula, and I'm going to construct the marginal distribution for y, and the values of y are -1, 0, and 1. This is fy, okay? So when y is -1, you need to add up all these values. 1/6 plus 1/3 plus 1/6. So that one is equal to 2/3. This is 2/3. Next, when y is 0, the probability here is 0. And when y is 1, you add up these probabilities, so it is 1/3. And clearly when you consider all these probabilities together, you add them up, the result should be equal to 1. Okay, so next, therefore EY is just substituting the values of y into this expression. We have -1 times f -1 plus 0 times f0 plus 1 times f1. And -1, f -1 is this guy, so this is 2/3. This one is automatic 0, and this is 1 times with 1/3. So we have -2/3 plus 1/3, so -1/3. Okay, what we're looking for is we're looking for covariance. Covariance xy is going to be equal to exy, which is 0. So 0 minus this one, ex is 0 times 1/3 negative, and the result here is going to be 0. So clearly the result that we get is covariance of x and y is 0. Now the purpose of this example is to show to you that even though the covariance is 0, it doesn't mean x and y are independent. So now how to prove that they are independent or vice versa. Okay, so this is what we're going to do. We are going to check. Okay, so now let's check the status of x and y. Are they independent? Okay, so now this small part right here is to investigate x and y independent. Now what's the idea of independence? If x and y are independent, then this result has to be true. Then fxy must be equal to fx times fy. So this is what it means when x and y are independent. And in order to check that, we can choose any values of x and y. For example, let's say I choose the value of x equal to 1, y is equal to 1. Okay, let's say this is what I choose. You can choose any other values, it doesn't matter. So in this case, I need to investigate what is f11. So f11 is okay, f11 according to the result given by this table is 1 over 6. So that's the value of f11. So the result is 1 over 6. Next, I need to know what is the value of what color? Okay, what's the value of f1? Okay, so what's the value of f1? f1 according to the table right here is 1 over 3. And then I need to know what's the value of fy when y is equal to 1. So this one is for x, yeah, x, and then I need to find the value. This one is corresponding to y, random variable. So when y is equal to 1, the result is also 1 over 3. Okay. Right now, if you multiply, okay, if I multiply the result here, 1 over 3 times 1 over 3, you multiply this result, what I get is 1 over 9. So the result is 1 over 9 on this side, and on the other side, for this one, the result is 1 over 6. So 1 over 6 is not equal to 1 over 9. Therefore, we know that x and y are not independent. Are not independent. Okay, so that's the idea. Again, let me just reiterate the important point. If x and y are independent, immediately the result here is true. Covariance must be 0. But the reverse is not true. That means if you get covariance xy equals to 0, it doesn't mean x and y independent. Doesn't mean x and y are independent. So that's the whole idea in this video. Okay, that's all for now. Thank you very much for watching.